How you guys doing today? Okay, just some administrative stuff while we're waiting for the people. Don't forget, homework 4.4 is still due today at midnight. The homework for 4.5 and 4.6 I changed to be until next week, in case you guys have an extra week on that stuff, but the 4.4 is due tonight. So make sure you've got that in place. That'll help you kind of think about things. There's some questions on 4.4 and talking to students in office hours. Some of the questions when they say, you know, for what values of x is this function gonna converge, its power series is gonna converge onto the function, you can go ahead and answer sort of, you know, in a hand wavy kind of qualitative way. You're learning chapter 4.5 is the ratio test where we actually find that radius and interval of convergence. So we're just trying to get you to think about it. In 4.4, you don't really have the skills to find it exactly. So just kind of hand wave, trying to pick values that are close to that so that you can get there, get close to it. Okay, so that's 4.4. Don't forget that's due tonight. We're going to finish up chapter 4.5 today. We have a bunch of examples to go through, and then we're going to start 4.6, which basically says, okay, now that you know that this function, this power series is equal to this function within this range, let's do mathematical stuff with it, like derivatives, integrals, addition, subtraction, multiplication, division, because we're going to treat it like any other polynomial. But let's just take a minute to remember our ratio test, okay, which we talked about yesterday. So we take the limit as n goes to infinity. We look at this next term up compared to the current terms. This tells us the trend. If I look at all of my terms in my series, what are they doing, right? Compared to one term to the next. The overall trend is that they're decreasing, right? Then I'm going to say that my series is going to converge, and it's going to converge towards my function, right? If each subsequent term gets bigger, okay, like the terms are not converging to a particular value, then I say that my series is going to diverge. If they're the same, right, it's equal to 1, the ratio of one term to the next is equal to 1. That means that they're not really changing. Then we say that this test, the ratio test, is inconclusive, okay, which means we have to learn other tests to be able to evaluate it, okay? So for us, what we're trying to learn and what we're trying to do with power series, we're going to see this. And when we start processing things, we're looking at what range of values will allow this to converge, okay? It's basically going to come down to our limit. Can we get our limit to exist or not in chapter 4.5? All right, so I've got my lecture examples for 4.5, okay? We went through a bunch of examples yesterday, and then we're going to finish up those examples today. Save your lecture examples for 4.5 because after we're done with chapter 5, we're going to come back to the lecture examples for 4.5 and 4.6 and then finish them out because we need to be able to lock down our interval of convergence. Okay. All right. So let's go ahead and keep going. So the ratio test only tells if is the series. That's correct. So the ratio test is going, so there's two things. So you'll see in chapter 5, we're going to use the ratio test to tell us that is it going to converge or not, right? We've got some kind of series that it's going to converge. When we use the ratio test on a power series is another name for a polynomial that represents a function, right? That we have derived specifically from a function so we can get these polynomial and the function to be equal to each other. When we use the ratio test on a polynomial, on a power series, then what we are trying to do is we are looking for a radius. We're going to solve our radius ratio test to figure out what is that radius around our center point, that plus or minus, that's going to allow us to say this, you know, Taylor series is equal to its function within this range of value. But you're right, there are certain series tests that we're going to learn in chapter 5 where we can actually get what does it converge to, and then some are just going to tell us if it converges or not. So yeah, that's a good question. Yes and no. Okay, I think I kind of answered that. There's a lot of stuff going on. Right now we're using ratio test on our polynomials, on our power series to help us figure out what's the radius of values around which this polynomial is going to equal to the function, okay? All right, so this one here, x to the n all over n, we're going to apply our ratio test. Okay, so when we do our ratio test, I'm going to say the limit as n goes to infinity. Everywhere I see an n, I replace it with an n plus 1. Give me just a sec. N plus 1. And this is going to be all over the original. And don't forget your absolute. Okay, so now I have a fraction divided by a fraction. I'm going to rewrite it, and I'm going to group the x terms, x to the n plus 1 all over x to the n. I'm going to group the n terms. I still have the absolute value. Okay, so now remember, x to the n plus 1 is the same thing as saying x to the n times x to the 1, right? If we break apart our addition here. So that means my x to the n's cancel, right? And I'm left with, and what I'm left with is go the limit as, whoops, I'm thinking of two different things, as n goes to infinity. As n goes to infinity, this is going to become x times n all over n plus 1. Okay, n is my variable inside the limit. That's what I'm taking the limit with respect to. So I can take out this x, and I've got the limit as n goes to infinity of n over n plus 1. So this right here, let's talk about it. If I'm just going to process that, the limit as n goes to infinity of n over n plus 1, right? My highest degree terms are the same, so I'm dealing with the coefficients. This thing goes to 1, okay? Now here's the tricky part, right? So basically our limit is equal to 1, right? So what this is equal to is absolute value of x. This is where I apply my criteria for convergence on the ratio test. This part here, let's write this down in a different color. This is our criteria for convergence on ratio test. Right, remember our ratio test where we said the conditions for convergence, right, that we just did this. To be less than 1, that means it's going to converge. I want it to converge. I want my thing, my power series to converge, and I need to find out what's the values around which it's going to converge. Now, this right here is my radius, okay? And also when I look at my power series right here, this is really x minus 0 to the n, right? X to the n is the same thing as x minus 0 to the n. Make sure this is in focus here. Okay, x minus 0 to the n, which means we're centered at 0. Okay, so let's conclude these things out. So I'm going to say my radius is equal to 1. My center is equal to 0. So now our interval of convergence, right, is going to be the center plus or minus, right, which is going to equal to -1 plus 1. Okay, now you haven't learned it yet. I'll give you the answer, right? We're going to learn how to do this, okay, after chapter 5. So to do this, I'm going to write down endpoint check. And I'm going to leave an empty space. See, look, here's my endpoint check, and look at that, the rest of the blank page, right? So I'm going to come back to this after chapter 5, and we're going to fill in this endpoint check with all sorts of stuff so that we can figure out, this is a closed bracket, that's an open bracket. I'm telling you the answer ahead of time, just so we don't just look like we have numbers, hanging out in the middle of nowhere. But from this, I can get my radius, I've got my center, and I've got my interval numbers, okay? After chapter 5, we'll come back and actually get the endpoints. Okay. Example 6. We want to find out what's the radius and interval of convergence for the following power series. Power series, polynomial, see it's an x. Okay, but when we do the ratio test, we're doing it as a function of n, right? I do the limit as n goes to infinity, absolute value, got my -1. Everywhere I see an n, I increase, I go n plus 1. X plus 1 to the n plus 1, all over 2 to the n plus 1, all over -1 to the n, x plus 1 to the n, all over 2 to the n. I'm going to extend my absolute value down. Okay. Fraction divided by fraction. So I'm going to, let's rewrite this. limit as n goes to infinity. Now I'm going to get rid of my minus ones because I've got an absolute value happening. So it's going to cancel out, get rid of my minus ones. So I'm going to ignore them. I'm going to group my x terms, x plus 1 to the n plus 1 all over, x plus 1 to the n times, right, 2 to the n all over 2 to the n plus 1, right? And then the minus ones are gotten rid of by the absolute value, okay? So now let's take a look, right? What's going to happen here, okay? So my x plus 1s to the n will cancel out and goes to infinity. So I'm going to be left with x plus 1 to the first power, times 2 to the n, so we'll cancel 1 over 2. Look, I don't have any n terms anymore, right? My n terms, what's the difference between if it starts at n equals 1 versus n equals 0? So in terms of, often when we talk about an infinite number of terms in our series, it often doesn't matter if we start with like an n equals 0, n equals 1, but in a lot of these cases, we're doing n equals 0 because I can, right? I can do a 0 because I have like 2 to the n, 2 to the 0 is equal to 1. Whereas if I start at 0 here, I'm going to get a divide by 0 error. So I have to be very careful, right? I don't want to introduce an error in my polynomial. So I have to start this summation at n equals 1 to make sure that I don't, like if this was n minus 1 in the denominator, I'd have to start at n equals 2 on my summation. So I didn't have a divide by 0 error. So you have to kind of be mindful of that. Okay, so no more n's, right? Let's do this. So I'm going to circle this. No more n terms, right? So to get this to converge, right, I'm going to go absolute value of x plus 1 divided by, I took the absolute value of 2, has to be less than 1. Okay. But now I get to multiply. I'm going to cross multiply that by 2. So then this becomes x plus 1 is less than 2. I don't do anything with this x plus 1 because look, that's where I'm centered, right? That's my polynomial is centered at x equals minus 1. So we think about that one. So my center, so I'm going to go x plus 1 equals 0, x equals minus 1, right? So this stays the same. I know that there are some ways to figure out my radius and my interval and stuff by adding and subtracting. We're going to leave it because this is where we're centered. This gives us our radius. Okay. Doesn't really make a difference. They'll just start at summation at 1 if they can't start at 0. Yeah, that's right. You just have to watch out for divide by 0 errors. Okay. So anyway, so here's our radius. So let's summarize this stuff. So I'm going to go radius equals 2. My center equals minus 1, right? We got that from our polynomial. Now our interval of convergence, remember, is our center, right? Our center minus the radius, center plus the radius. So I'm going to go minus 1, minus 2, minus 1, plus 2. So this is going to be minus 3 to 1. Okay. I'll tell you the answer ahead of time in terms of the boundaries, right? So this is going to not include either, but we need to do an endpoint check, which we'll do after chapter 5. So I'll just write down endpoint check. We haven't got there yet. We'll get there in a few weeks. How do you get the radius again? How do I get the radius? It's a fundamental question. It comes back from the nature of our ratio test, okay? Our ratio test, let's take a step back completely. Our ratio test says, fundamentally speaking for power series, right? I check my next term up to my current term. That's what we're doing here. Next term up to our current term, right? I have to compare this. I'm taking the limit as my n goes to infinity, right? I want to keep looking at all of these terms in our series. This is an infinite series, right? It sums all the way up to infinity. So we're looking at, as n goes to infinity, what are each subsequent terms doing? Are they converging to a particular value or not, right? To get this series to converge, this ratio of the next term up to the current term has to be less than 1. This is your criteria for convergence. If it's greater than 1, it's going to diverge. Okay, so I go through all of my limit stuff. All of this stuff has to be less than 1 because I want my power series to converge. So if my limit exists, right, let's say for example, I ended up with an n in the numerator. As n goes to infinity of n, that's going to be infinite. So my limit will not exist. If my limit doesn't exist, that means this power series converges only at a. Okay, we have a radius of 0. It converges only at our a point. This right here, this 1 comes from the definition of our ratio test. Okay, I had a leftover 2. Okay, that was from when I cleaned up this 2 to the n. I had this leftover 2. I keep this x plus 1 as a block because that represents my polynomial. We're centered at x equals minus 1. So I'm going to multiply this whole thing by 2 to find the radius. Now x plus 1 is less than 2, right? So that gives me a radius of 2 around my center point. So within the values of x equals minus 3 to positive 1, this polynomial will sit on top of whatever function it represents. Okay, that's how we got this. Don't go hog wild and subtract the 1 from both sides or whatever, leave it. Okay, we're finding the radius. We know the center from the polynomial. We're going to subtract, add and subtract to get the interval. I put it in red here because we haven't learned how to do the endpoint check yet. We'll know how to do that after chapter 5. Okay. All right, the last example. So what are the radius and interval of convergence for x to the n all over n squared? All right, let's go ahead and do this. So our ratio test. Okay, so I'm going to go the limit as n goes to infinity. Okay, my absolute values. This is going to be x to the n plus 1 all over. Be careful, this is n plus 1 squared. All over x to the n all over n squared. So I'm going to multiply by its reciprocal. Right, so this is going to become, let's group like terms together. So x to the n plus 1 all over x to the n times n squared, n plus 1 squared. Okay, so this cleans up the limit as n goes to infinity. This is going to become x times n squared, n plus 1 squared, which now that I have this, I'm going to bring it outside my limit. And I can do that because there's no n attached here. This limit corresponds to my variable n. Okay, so I'm dealing with n squared all over n plus 1 quantity squared. Okay, so in order for this thing to converge, it has to be less than 1. So let's take a look. Right here, when I take the limit as n goes to infinity of n squared over n plus 1 quantity squared. I have an n squared in the numerator, n squared in the denominator. Coefficients, leading coefficients went out. This thing goes to 1. My limit goes to 1. So what we're dealing with is absolute value of x is less than 1 for it to converge. Because that's what we're looking for. We want to know where it's going to converge. So that tells us our radius. Radius is equal to 1. Our center, I read here, x minus 0. And I'm going to use that to come up with my interval of convergence. Right, center plus or minus my radius. Okay, and I'll tell you what the boundaries are, even though we don't know yet how to do that. These are both included. But I will put a little thing, endpoint check. Okay, we haven't got there yet. Okay, so that's 4.5. 4.5 tells us how to do the ratio test and how to apply it to power series. We want our power series to converge. What does it mean if a power series converges? It means that that power series, we can use the power series and the function equivalently. Power series will converge on its function between x equals minus 1 and x equals 1. Okay, it's like those graphs that we've always been making, right? So if I'm centered at 0, positive 1, and I've got my functions doing something, my power series is doing something, they're essentially equal to each other within this range of values of x. Okay, right. You can graph these out. I like to graph them out on my calculator and take a look. See how they sit right on top of each other. within certain ranges, within certain values of x. Okay. All right, so hold on to these. We're going to come back to them again after chapter 5. All right. So with that said, let's talk about chapter 4.6. I've got my lecture examples for 4.6, and I'm going to pull those out in just a minute. Is it possible if we can do one of the problems from the 4.5 homework? Do you know if we have time at the end of class, although it's probable that we won't have time at the end of class, although I think 5.1 is relatively straightforward. So on Monday, if you guys, I highly suggest you guys take a look at the homework for 4.5 and 4.6 over the weekend. And then on Monday, we can talk about homework problems for 4.5 and 4.6. But let's see how we're doing on timing for 4.6. I think we may not have time to talk about homework today, but we can talk about it on Monday. Okay. All right, so chapter 4.6. This is power series as functions, part 2. Okay, and then the subtitle here is, isn't it great we're dealing with polynomials, because then we can do derivatives and integrals nice and easily. Differentiation and integration of power series. That's what basically we're going to focus on, but we can also do addition, subtraction, multiplication, and division too. Okay, I'm not sure if we'll get to these today, but we're definitely going to get to derivatives and integrals, which, as you know, if we're dealing with a complex function, if I can reduce that complex function down to polynomials, taking the derivative or taking the integral is nice, because I'm just doing the power rule, right? It's a polynomial. So let's remember our power series represents a function, f of x. Okay, which means I'm going to enumerate this out. So it's going to look like c sub 0, c1, oops, x minus a squared, plus c3, x minus a cubed, plus so on and so forth. Okay, so that's our function, generically speaking, as a power series. If I go to take the derivative, so let's do this. If I go to take the derivative, I'll say my function is differentiable and therefore continuous. Okay, so if it's differentiable, I'm just going to do the power rule because it's a polynomial. But let's remember, how do I do the derivative in series in my summation form? So I'm going to go like this. N equals 1 to infinity. So I take my exponent, bring it down, multiply it by the coefficient that's there. I've got my x term, and I subtract 1 from the exponent that was there. That's it, right? My power rule. If you forget or you don't have the summation form, you can take the derivative of your polynomial, right? Which is going to be, if I take the derivative of constant term, that's just 0. Plus, I'm going to go c1 times 1 plus 2, my exponent, times c2, x minus a to the first power, I'll write the 1, plus 3 times c3, x minus a squared, plus so on and so forth. Okay, I just did the power rule for derivatives. See, polynomials are nice, right? All right, my second option is my function is integrable. Okay, so in this one, we're also going to do the power rule. Make sure when you do this, we're doing f of x dx. When we did our ratio test, we did it with respect to n, but here we're integrating and we're deriving. This is like dx. We're taking the derivative with respect to x, which means n is just like a constant term. It's just a coefficient, okay? So keep that in mind, all right? Also, I'm taking the integral of my function, not the integral of my derivative, but the integral of my function. So we're going to do the power rule again. So let's do it both in summation form and we'll do it individually. Okay, so summation form says, well, ooh, I can't forget. So I've got C. Let's try C, and I'm going to write this in red. This is my constant of integration. Okay, your constant of integration, we're going to talk about how we can actually solve for that. But for now, make sure you always have your constant of integration. Okay, and now here's my summation. Plus sum n equals 0 to infinity. What am I going to do? I've got my coefficient that stays the same. I take my x term, I increase the exponent by 1, and then I divide by the new exponent. Power rule for integration, constant of integration here. Okay, so this is equal to C. This is our constant of integration here too. So let's write there and there. Okay, oops, sorry. So what am I doing? I'm doing this. I'm going to take the integral of each of these individual terms. Maybe I don't have the summation form, but I'm going to take the integral here, integral here, integral here, integral here. Okay, so I've got my constant of integration plus, right? I'm going to go C0, x minus a to the 1, plus C1, x minus a squared all over 2, plus C2, x minus a cubed all over 3. Okay, plus so on and so forth. Okay, power rule. Boy, polynomials are nice, right? I can solve for my C, my constant of integration, by plugging in essentially what is x equals a into my function, as well as into here, into the polynomial. Basically, I'm just going to be able to find out what that is. We'll do some examples like that so you can see what it looks like. Okay. I'll let you guys finish writing that, and then we're going to talk about the radius and interval. Okay. All right. So each function f of x has a radius of convergence, right? And an interval of convergence. Okay, this is our ratio test, right? Where we want everything to be, our radius is going to be greater than 0, right? We want to figure out what that, radius of convergence is. The interval of convergence is going to be our a minus our a plus r, right? Where we're centered. And this is just a parentheses just for us to keep it quiet, but like this is, we may have, combinations, right? We have to do an endpoint check to figure out where things are. Okay, so now every function has a radius and an interval of convergence. So let's say f of x has an r and it has an interval. When I take my derivative or my integral, right, I have the same radius, okay, and you have the same numbers in the interval, but with the interval, the boundaries, whether it's included or not, right, may change, okay? Which means for both of these, right, I'll have to redo the endpoint check to see is it a closed bracket or an open bracket, okay? This part right here, our boundaries, we're going to cover after chapter 5. But when we do these, the function, the derivative, the integral, we'll be able to calculate out the radius, and we'll be able to calculate out the numbers for our interval of convergence. And then we come back after chapter 5, we're going to look at the boundary check, okay? It's a lot to take in, but you can do it. All right, so let's just put a little star before we jump into examples. We'll say, in this way, right? Our power series behaves just like a polynomial. A function defined by a power series behaves a lot like a polynomial. And polynomials are great because I can do the power rule on them, right? It's easy to do math operations on polynomials. Okay. Once you guys finish writing that, take out your lecture examples for 4.6. I think there may have been a typo. I corrected it, but I think yours online may still say 4.5. But it's 4.6. You might want to change that. Okay, so check, make sure that number is correct. Okay, all right. So now we want to look at, we're just looking at what's the derivative. We're not going to worry about radius or intervals or anything. We're just looking at how do we take the derivative. So the first thing I'm going to do is I'm going to enumerate out a handful of terms, like 5 terms. And then so I can check to see if I did my summation derivative correctly, because I can always take the derivative from my first handful of terms in my polynomial. So when n equals 0, I'm going to get 1. When n equals 1, I'm going to get x. When n equals 2, I'm going to get x squared all over 2 factorial. Right, and so on and so forth. Okay, all I did was say n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. Okay, so just enumerated out what this thing looked like. Okay, so let's do this. What's the derivative? So let's call this f of x equals that. So my derivative, we'll do it first with the summation and then with our individual terms. Okay, so summation. I'm going to go n equals 1 to infinity. So to do my derivative, I'm going to do the power rule. So I take my exponent and I subtract 1 from the exponent. And I have this 1 over n factorial is a coefficient, okay? But n factorial, right? So n factorial is equal to n minus 1, n minus 2, so on and so forth. So the n's cancel out. So this is equal to x to the n minus 1 all over n minus 1 factorial. And I have to start now at n equals 1, because if I were to plug in, right, if I were to plug in n equals, I'm going to get n equals, if I plug in 0, I'm going to get minus 1 factorial, which isn't going to be correct. So I have to start here. 0 factorial is equal to 1, so we're okay with that. All right, so now think about what we just did. So let's enumerate. I'm going to take my derivatives from here just to check to see if it's right. Derivative of 1 is a 0. Here is 1. Right here is 2x all over 2 factorial. Plus, this is going to be 3x squared all over 3 factorial. Plus 4x cubed all over 4 factorial. This is equal to 1 plus x squared over, 2 factorial plus x cubed all over 3 factorial plus so on and so forth. Looks familiar, right? Hey, what function is equal to its derivative? What function is equal to its derivative? Must be e to the x, okay? So e to the x is a function that's equal to its own derivative. So we're looking at that there. You won't necessarily be asked to identify things, but I'm kind of pointing it out so that you can recognize it when you see it. Okay. Let you guys finish writing that and then we'll do example 2. We're not checking endpoints or radius here because we weren't asked to. So we're just trying to get into the swing of things in terms of taking the derivative. Okay, find the intervals of convergence for our function, its derivative, and its integral for this following power series. All right, so because the radius of convergence is the same between the function, the derivative, and the integral, I'm going to find the radius of convergence and the interval, the numbers for the interval, okay, for my function first. And then I'm going to look at the derivative and the integral, because then I can just apply. I don't have to take the radius. I have to do the ratio test on all three of these things. I only have to do it once on my function. Okay, so kind of think about how you're going to consolidate your work. So let's do our ratio test first. Test for radius and interval. Okay, so our ratio test says we're going to go the limit as n goes to infinity. Be careful. Ratio test is a function of n, right? Because we're looking at all these terms in our series. Whereas when I take the derivative and the integral, it's a function of x. Okay, so the limit, I'm going to go x to the n plus 1 all over n plus 1, x to the n all over n. So this is equal to the limit as n goes to infinity. Let's group them together. N plus 1, x to the n, times n all over n plus 1. Okay, so this is going to become absolute value of x times the limit as n goes to infinity. Absolute value of x comes from this, simplifies down to x. This is times n all over n plus 1. This here, this limit right here, as n goes to infinity, this thing goes to 1. Same degree, coefficients are going to dominate. Okay, in order for this to converge, it has to be less than 1. Okay, so we're summing up to converge. So let's write this down. We have a radius equal to 1. Our center comes from here. Our center is equal to 0. So our interval is equal to plus our center plus or minus our radius. Okay. Now on my function, I would need to do an endpoint check to figure out, are these endpoints included or not? So what I'm going to do is I'm just going to leave myself space to do that after chapter 5, but I'll tell you the answer for that. Let's see, for f of x was, this is included and that one's not. Okay, you don't know why yet. I'm telling you the answer ahead of time. We're going to come back to it later. Okay, so now let's do our derivative and our integral. Okay, so my derivative, I'm looking here. I can enumerate out the first handful of terms and do that too. So let's do this. I'm going to do f of x. I'm going to enumerate out the first handful of terms. So the first term is x, right? The second term is going to be x squared over 2, x cubed over 3, x to the 4th over 4, x to the 5th over 5, right? And so on and so forth. Okay, so when n equals 1, n equals 2, n equals 2, this is what this thing looks like. Okay, I just enumerated that. So we kind of have that to think about, right, as we're going to do our derivatives. It's too bad I can't scroll down very well. Okay, so I'm going to do first my derivative on the summation, and then we'll check it by doing the derivatives on the terms. So summation n equals 1 to infinity. So I have to bring down my exponent, x to the subtract 1, right? And then I have my 1 over n was there from before. Okay, so that kind of gets carried through. So then this, I'm going to clean this up. N equals 1 to infinity, x to the n minus 1. Okay, let's just check it. I'm going to take the derivative of all of these terms here. Okay, so this is going to be the derivative of x is equal to 1. The derivative of x squared over 2 is equal to x squared, x cubed, x to the 4th, and so on and so on. Okay, and if I take the derivative of all of these terms here, okay, which is what we're seeing here. Okay, so it comes out, we did it right. Okay, my radius is the same as with my function, which is equal to 1. My center hasn't changed either. I'm still centered at 0. My interval still has the same numbers. To find out what the boundaries are, I have to do an endpoint check. Okay, I'll tell you, we're going to leave space, but I'll tell you on my derivative, my endpoint check comes out to be neither one's included. So it changed, right? This one was included. It's not anymore on my derivative. Okay, so this is my derivative. let you guys, you don't know this yet. I'm telling you the answer ahead of time. You don't know what it is. I'm leaving a blank space to do my endpoint check. Okay. I'm going to do an integral of f of x. It means I'm going to integrate this. Be very careful. It's a common mistake. People integrate this because they're rolling right along, but you go back to your function. It's the integral of f of x, not the integral of f prime, integral of f. Okay, so let's go ahead. So I'm going to go integral of f of x dx. It's important to remember it's a function of x. So all of those n that we have, those are just like constant terms that I get to bring through. So the first thing I have to do is have my constant of integration. Plus, I can look at my summation, right? So I'm doing a summation, oops, n equals 1, sorry, to infinity. Now, we're doing the power rule. So we have originally x to the n all over n, which means I'm going to go x to the n plus 1 all over my new exponent times 1 over n, right? 1 over n is what we had before. This is our power rule for integration. This is my constant of integration here, okay? What happens is we can get rid of our, we're going to talk about this, our constant of integration we're going to be able to solve for later, but we're going to not worry about it so much right now. So my radius is equal to what we had before, which was equal to 1. Our center is the same as before. And our interval, minus 1 to 1. Okay, I'll tell you this. Okay, you don't know that. You don't know why yet. We have to do an endpoint check, which I'm going to leave blank for now because we don't know how to do it yet. After chapter 5, we will. Okay. All I did was power rule on my summation. Okay. It would be the same thing as if I integrated each individual term. Okay. My polynomial. Okay, guys. All right. So this is a neat example. It's sort of a little bit straightforward, but I mean, like we could easily, so we want to find the power series for ln of x centered at a equals 1. Now, technically speaking, we can come up with our Taylor series for ln of x, right? We're going to show you how you can derive it by using a different power series, by integrating a power series to get there. Okay, so this is what we're going to be doing, finding a power series by integration. So let's just write it like this. So if f of x equals ln of x, the derivative of ln of x is 1 over x. Okay, so let's say you had a power series for 1 over x. I'm going to give it to you, and then I'm going to show you where it actually comes from. N equals 0 to infinity, minus 1 to the n, x minus 1 to the n. This is basically, it's an nth order Taylor, okay, for 1 over x. I'll derive it. I'll do it in a different color just so you can see where that comes from. Okay, where I'm actually getting that. So I'm going to go with my function. I'm losing ink. Okay. So if my function is equal to 1 over x, and my a is equal to 1, 1 over 1, my first term is equal to 1. My first derivative is equal to minus x to the minus 2, right? So my a equals 1, if I evaluate that, I'm going to get minus 1. My second derivative is going to equal positive 2, x to the minus 3. And I go to evaluate that here. This is equal to positive 2. This is basically f of a equals 1. Okay, so then third derivative, right? I'm going to get minus 3 times 2, x to the minus 4. This is going to become minus 3 factorial. After the fourth, that's a 4, is equal to positive 4 times 3 times 2, x to the minus 5. This is equal to positive 4 factorial. Okay, so on and so forth. Okay, dot, dot, dot. We can come up with the rest of it. So now I can put this together into a Taylor series. Okay, so my first term is 1 minus, this is centered at 1, so x minus 1, this is going to be times minus 1, that's where that negative comes from, plus, okay, now watch what happens. My coefficient is 2 times x minus 1 squared all over 2 factorial, plus a minus 3 factorial all over x minus 1 cubed all over 3 factorial, plus 4 factorial, x minus 1 to the 4th, all over 4 factorial. Remember, this denominator comes from our Taylor series. Okay, so let's clean this up. This is equal to 1 minus plus x minus 1 squared plus, I'm sorry, this should be a minus, x minus 1 cubed plus x minus 1 to the 4th minus, okay, good, alternating. There. Okay, so that's basically what we have here. Okay, right, so we're starting, I'm telling you like how it's derived. I just gave it to you, but I derived it so you can see where it came from. Okay, so now this is our power series for 1 over x. 1 over x is our derivative for ln of x. If I integrate my derivative, I'm going to get my function, right? So this is what we're going to do. We're going to integrate our, this is 1 over x dx. If I integrate, that's integrating my derivative, which is going to give me ln of x. Okay, so let's think about it. I'm going to integrate okay, with respect to x. We're doing it with respect to x, so n is just a variable. It's like a constant, I'm sorry, not a variable, it's just a constant term, okay? It's my exponent, it's my summation variable. Okay, so when I go to integrate this, what do I get? I get my, since we're gonna say it's ln of x, but I'm gonna get my constant of integration plus my summation, okay? This is gonna go n equals 0 to infinity, minus 1 to the n still, x minus 1, I have to increase this by 1 and divide by my new exponent. This is my power rule for integration. Okay, so let's do with our constant of integration. So I'm going to say when x is equal to 1, right? I plug in x equals 1, I plug in x equals 1, c equals 0. Okay, so now in that way, I can then say natural log of x is equal to summation minus 1 of n, x minus 1 to the n plus 1, all over n plus 1. So in this way, I came up with a power series for natural log of x by integrating the power series for 1 over x. It was easier. Okay, we would then do a ratio test. Okay, which we'll do offline. You guys can do it offline. We're gonna find our radius is equal to 1, okay? If our center is equal to 1, then the interval is equal to 1 minus 1, 1 plus 1. So we're gonna go from 0 to 2. 0 to 2 tells us the range of values of x over which this polynomial converges to ln of x. So between x values of 0 and 2, I can use this polynomial instead of ln of x. That's nice. Okay. Oh, I'll give you the boundaries on it too. It looks like this and like that. We would have to do an endpoint check. To get that, which we're not doing right now. Okay. Let you guys finish writing that, and then we'll talk about some mathematical operations we can do on series. Okay. All right. So operations with polynomials. Oops. Oh, call it power series. So these are like mathematical operations we can do with power series, which are polynomials, right? So first, let's just say f of x is equal to n equals 0 to infinity, a sub n, x to the n, some power series. G of x is a different power series, b sub n, x to the n. This is just like a, you know, we want to be able to represent, say f of x and g of x are power series. They're infinite polynomials. So the first thing I can think about is f of k times x. If I were to substitute kx in for x, right, what am I going to be getting? I'm going to sum n equals 0 to infinity, a sub n. Think about what happens. I'm going to go k to the n, x to the n. These are just, we're playing around with exponents and substitution. If I were to substitute x to the capital N, some other exponent, into my x to the little n, x to the n times n. Like these are, we're playing around with how our exponents work with each other. So if I wanted to add or subtract g of x, I can do that in my series. I can add and subtract like terms on my series, okay? These are just some things that we can do. This one, example 4, I put in here right now, but we're gonna come back to this one after chapter 5 because example 4 actually deals with a couple series types that we're gonna introduce in chapter 5 that it won't make much sense if I go over it now. So we're gonna come back to example 4. So I'm gonna skip this. We'll do this one later in a couple weeks from now. Okay, so let's talk about this one. Example 5. So I'll find the first 3 non-zero terms of the Maclaurin series, e to the x arctangent of x, okay? So if I wanted to, I could do this out the long way, right? I mean, my derivatives are gonna explode, right? Because the first derivative I have to do with a product rule. My second derivative is gonna have product rules and quotient rules. I've got a lot of things to deal with, okay? So we wanna be able to think about using substitution to work with it. These, you want to see the operations in the, yes, there. So substitution problems, I'll leave it like that. So substitution problems, there's always like a question like this on the final exam, right? Where you need to be able to come up with, you know, some kind of expression. Like we're going to ask you to come up with a Maclaurin series or Taylor series or whatever, Maclaurin most likely, for a function like this, right? You're going to come up with that polynomial, and then we're going to ask you to take the integral or take the derivative of it. Okay, and then evaluate that at maybe some value. If you don't use substitution, one, you're going to get that first part of the question wrong, and you're also going to be spending a lot of time trying to come up with this derivative, and you might make a mistake and come up with it wrong. Okay, so always, if you can, unless you're told not to, be thinking about how you can use substitution. Okay, so let's go ahead and think about that right now. So our Maclaurin for e to the x is equal to 1 plus x squared, 2 factorial, x cubed, 3 factorial, x to the 4th, 4 factorial, so on and so forth. And that's basically equal to x to the n all over n factorial, right? Our tangent, now remember the Maclaurin for these two functions in particular is equal to, for all values of x, the Maclaurin is equal to the polynomial, is equal to its function. For all values of x for our tangent, our Maclaurin polynomial is equal to the function. So these have like an infinite radius. Okay, that was somebody else that proved that. I think we talked about that a couple of chapter sections back. Cubed over 3, x to the 5th over 5. Oops, sorry, there's a negative in there. Negative, x to the 7th over 7, plus x to the 9 over 9, so on and so forth. And this is basically equal to minus 1 to the n, x to the 2n plus 1, all over 2n plus 1. Okay, so these are our Maclaurin for our functions. Okay, so now e to the x, I'm going to substitute in my Maclaurin. Our tangent, I'm going to substitute in my Maclaurin. And I'm going to do polynomial multiplication. Okay, so we're going to say e to the x, arctangent of x, looks like this. E to the x, 1 plus x squared all over 2 factorial, x cubed all over 3 factorial, x to the 4th all over 4 factorial, plus dot, 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 times arctangent x minus x cubed all over 3, x to the 5th over 5, x 7th over 7, x to the 9th over 9, so on and so forth. Right? So look what I did. I substituted. This is the Maclaurin for e to the x. This is the Maclaurin for arctangent. Now, the fun part begins where you have to multiply all of these terms together and then add up the like terms. It gets to be messy. Give yourself plenty of room and check your answers. Okay, so I'm going to multiply these out. So if I go 1 times, right? So I'm going to go, I'm going to get x plus x squared plus 1/2 x cubed, 1/6 x to the 4th, 24th x to the 5th. And I'm actually like not really going on for very long when I'm doing this stuff. Okay, so because I don't want to, I don't feel the need to, you know, have like all these terms like way out to like the 12th power. I don't worry about that. I'm just going to go out to maybe the 5th power. Okay, but then when I multiply the next one out, I'm going to get minus 1/3 minus 1/3 x to the 4th minus 1/6 x to the 5th plus 1/5 x to the 5th plus, and so on and so forth. You can keep adding it up. And then I'm going to sum up all the like terms. Okay, so it's going to give me x plus x squared plus 1/6 x cubed minus 1/6 x to the 4th plus 3 over 40 x to the 5th plus so on and so forth. And that is equal to e to the x arctan of x. Okay, this is the Maclaurin. Maclaurin for it. If you guys want to stay for like 5 minutes after class, then we can talk about homework stuff. Okay. Okay. All right. That's this one. We can do the last example. Example 6. Find the first 3 non-zero terms in the Maclaurin series f of x tangent of x. Now, if I wanted to actually come up with the Maclaurin series for tangent of x, I could, right? But my derivatives, after the first derivative, it's going to get complex pretty quickly, right? I'm going to have a lot of terms floating around, and it's going to be a pain. So I'm going to think again, substitution. Okay, so my f of x is equal to the tangent of x. Remember, tangent is sine of x over cosine of x. I'm going to substitute in my sine of x Maclaurin, which is x minus x cubed over 3 factorial, x to the 5th over 5 factorial, so on and so forth, all over my Maclaurin for cosine, squared over 2 factorial, x to the 4th over 4 factorial, so on and so forth. Okay, so now what I have is polynomial long division to come up with the Maclaurin for the tangent. Okay, which we can do that. So let's take, I'm going to go 1 minus x squared 2 factorial plus x to the 4th all over 4 factorial divided into this right here. Now what I need to do is I actually need to put in like my phantom terms probably. So I'm just going to write it out. This is going to be x minus 1/6 x cubed plus 1 over, what do I have? This should be 120 x to the 5th. Okay, and so on and so forth. Okay, so now I'm going to divide through this by that. I'm going to get x times, this is going to be x minus 1/2 x cubed plus 1/24 x to the 5th. And I'm going to flip all the signs. And I'm going to add, okay, which is these are going to cancel. And I'm going to be left with 1/3 x to the cube minus 1/30 x to the 5th, so on and so forth. Okay, now I'm going to divide this into here, and I'm going to get 1/3 x to the cube. So I'm going to multiply through. So on and so forth. Flip the signs, and I'm going to add. And then I'm going to get 2/15 x to the 5th, so on and so forth. So I can keep going. So this is going to be plus 2/15 x to the 5th. So depending on what your order is, right? Let's do just the 5th order. Maclaurin for tangent of x is going to look like this. X plus 1/3 x to the 3rd plus 2/15 x to the 15th plus so on and so forth. Okay. Remember before we did arctangent, this is tangent, which is just sine divided by cosine. Sine divided by cosine. Okay. Polynomial division. Okay. Phew. But once we reduce things down to polynomials, it just becomes polynomial multiplication, polynomial division, integration and derivatives of polynomials. It becomes much more straightforward. Okay. All right, guys. I think if you want to stay, this is it for 4.6. If you want to stay, we can answer a couple questions for the homework. It looks like there's a homework question on 4.4. If you guys want to stay and listen to that, you are welcome to. Just let me get out my notes for 4.4. my homework. Oops. And have a great weekend. If you guys don't want to stay, that's fine. Okay, so which one was it? Number 5. All right, so number 5 says, recall, so using this, we see that can be approximated, yeah, without using L'Hopital's rule. Okay, so let's do this one. So this is, let me get out my pencil. So this is chapter 4.4, question 5, homework. Okay, so we're given that ln of 1 plus x equals x minus x squared all over 2, x cubed over 3, x fourth over 4, x fifth over 5, x sixth over 6, and so on and so forth. And we're shown that they say that minus x plus ln of 1 plus x divided by x squared is best approximated when x is close to 0. So as x goes to 0, what constant term best approximates that? So this right here, right? Look at what we did. We subtracted x from here, right? I divided by x squared. So what's left over here is going to be equal to minus 1/2. It's going to be minus 1/2 plus x cubed plus all these terms. So I'm going to divide, yeah, it'll be like x. Let's do this, x cubed divided by x squared over 3, and so on and so forth. Okay, but it's best approximated by the constant term there. This is all on, if you want to see these, but you have to go to class. This is all on our recording. So if you want, you can take a look at the recording for the lecture, which I'll post as soon as I get it. And then it'll be right at the end. Probably you can look for it. Okay. So here, so this is part A. So 1/2 is what's left over. It comes from right here after I subtract x and divide by x squared. Okay. Part B says I've got the limit of this thing here. So the limit as x goes to 0 minus x plus ln of 1 plus x all over x squared. And so as x gets close to 0, right? And you can't use L'Hopital's. Like normally we'd use L'Hopital's and see what was going on, right? But they're not going to let us do that. No L'Hopital's. So what you can do is a brute force where I'm going to choose a value. Choose x to some value that's really close to 0, so 0.001 or 0.0000001, however many zeros you want, and plug it in, right? So I'm going to go minus 0.001 plus ln 1 plus 0.001 all over 0.001 squared, and then do it out. So if I do that, I'm going to go minus 0.001 plus natural log of 1 plus 0.001 divided by 0.001 squared. And then what I get when I plug that in, I'm going to get minus 0.4999 or 9966 something, whatever, which is basically like minus 1/2. If I chose a value for x that was even closer to 0, like if I had 10 zeros and a 1 or something like that, I would get it even closer to, closer to 1/2. Okay. Does that help? Also, just take the limit as the series approaches x, since the terms with x would be 0 and only a minus 0.5 would remain. Where would you get 0.5 from? So if I do take that, let's do that. So if I'm going to go the limit, x goes to 0. So I'm going to get, let's distribute these together. So I'm going to go minus x over x squared plus ln 1 plus x all over x squared, right? So what am I going to get? This is going to be the limit, x goes to 0. This is going to be minus 1 over x. So I need L'Hopital's, right? Because this is 0 over 0, that's indefinite. So I can't actually take, like basically what's going to happen is if I plug in as x goes to 0, I'm dealing with 0 over 0 plus 0 over 0. This is an indeterminate form, which means I need to use L'Hopital's in order to evaluate the limit. So I don't know how I can take the limit without using L'Hopital's. And I think take the limit of the expanded Maclaurin series. Oh, so take the limit of this. Yes, if you take the limit of that as x goes to 0, 0.5, you mean of this right here? Take the limit of, oh, I see, of this right here. Yes, yes, exactly. So this term here, right? Basically what's going to happen is everything else is going to go to 0 and what you're left with is minus 1/2. That's true. So you could substitute instead of this, you're taking the limit of both sides. Is that what you're saying? That works too. I just did brute force, but that works too. Yeah. Any other questions, you guys? You can probably have time for one more question if you have it. 13 from 4.4, sure. Let me read 13. Okay, so can you determine, okay, yes, so 13. So let's go ahead and take a look. All right, so 13. So let's do 13 out. So 13 is, so this is 13 from chapter 4.4. So we've got f of x equals ln of 1 plus x, and we're saying a equals 2. So I'm going to set up my my derivatives and my evaluations. I'm going to create the Maclaurin, my Taylor for it. So my function, and then x equals a equals 2. Okay, so my function, oops, of x, ln 1 plus x. So this is going to be ln of 1 plus 2, which is the ln of 3. Okay, so my first derivative, we're used to thinking Maclaurin where that first term is going to be 0, but look, it's ln of 3. So my first derivative is 1 over 1 plus x, which let's write it like this, 1 plus x to the minus 1. So this is going to become 1 over 1 plus 2, which is equal to 1/3, right? My second derivative, right, is going to equal to minus 1 plus x to the minus 2. So this is going to become minus 1 plus 2 squared, so minus 1/3. I think it's basically 1/3 squared, but negative cubed is going to equal to positive 2, right? Because minus times minus, 1 plus x to the minus 3. So this is 2 all over 3 cubed. Okay. After the fourth. Did they say how far up to go? I guess I went up to the 5th. All right, so this is going to be minus 3 times 2 times 1 plus x minus 4. So this is minus 3 factorial all over, this is 3 to the 4. I could clean that up, right? I could cancel out one of those three, so I'm just going to leave it for now. After my fifth derivative is going to look like positive 4 factorial minus 5. So this looks like 4 factorial all over 3 to the 5. Okay, so these give me my coefficients. Okay, so we're going to add this out, and we could go on and on, but they didn't tell us where to stop. So I just did like the, you know, the first handful of terms. So my Taylor looks like my function evaluated at A plus 1/3 x minus 2. My center is at 2, right? X minus 2 plus, this is a minus 1 over 3 squared times 1 over 2 factorial x minus 2 squared. Can you see that okay? Plus, that's this one, right? This 2 factorial comes from our Taylor series expansion. Okay, I could, let's draw it like this. 2 factorial. Okay, this is our coefficient. This is our Taylor series. The next one, right, let's keep track. The next one is going to be 2 over 3 cubed times x minus 2 cubed all over 3 factorial. Okay, plus our next one, minus 3 factorial all over 3 to the 4th times x minus 2 to the 4th all over 4 factorial. Plus, I'm not even worrying about keeping these straight. So plus 4 factorial all over 3 to the 5th times x minus 2 to the 5th all over 5 factorial. Now I can clean these up, right? But I'm not going to worry about it. It just looks like that for here. So this, right, let's make it look nicer. So I'm gonna clean it up now. So ln of 3 plus 1/3 x minus 2 minus 1 over 18 x minus 2 squared plus 1 over 3 to the 4th. Sorry, wait, did I goof up? 3 squared cubed. Okay, this is a cubed. Yep, 3 x minus 2 cubed minus 1 over 4 times 1 over 3 to the 4th x minus 2 to the 4th plus dot dot dot. I guess I could do that one too. I didn't do it before, but I'll do it again. 1 over 5th, 3 to the 5, x minus 2 to the 5 plus dot dot dot. Okay, so this is our nth order Taylor for ln of 1 plus x centered at a equals 2. Phew, that's a pain, right? But we can do it. So this is part A. Part B says the Taylor series centered, where does it converge? Technically speaking, we need to do the ratio test, right? I need to summarize this into some kind of summation format and do it. Ratio test, but since we don't know it, I'm going to do a graph. I did a graph. So what I did was I graphed both. So I graphed my function ln of 1 plus x, and I graphed, this is actually, when I did it, I only went up to, let's see, second, looks like I went up to the third. I just did the third order, okay, because I got lazy typing it all in. So when I graphed it out, basically what happens is I got this, right? Let's do this. I'll set this equal to, let's see, 3. So let's graph it. So this is our ln. That's our function. And here comes our Taylor. It sits right on top of it. You don't see it. It sits right on top of it. And then it starts to pull away. So basically we're doing good from, I would say, you know, somewhere maybe around x equals a half to about 1, 2, 3, 4, x equals 4. Okay, so my range of values by the graph. So let's see, 1/2 is less than or equal to x, which is less than or equal to 4. By graph with the third order. Okay, I'm sure if I did the 5th order, my range of values would expand. Okay. Phew. All right. Okay. All right. I need to sign off, and I hope you guys have a great weekend. Okay, I'll post this video so you can have it to take a look at a little bit later. Okay. Take care, guys.
Thank you.
Thank you.
Have a great weekend.
Thank you.
Thank you.
Bye.